Okay, year 12, so I just thought I would go through the second entropy quiz and the last homework from topic 13b, because quite a few people were starting to struggle with some of the ideas. So we'll see what's going on. First, which process produces a decrease in entropy of the system? Well, the first one's producing a gas, so it's definitely not that. That would be a big increase in entropy. On this one, you've got a solid becoming a liquid, so that's an increase in entropy, so it definitely isn't that one. And on this one, you're also producing a gas, so it definitely isn't this one. So it must be C. And why is it C? Well, you're going from 3 gas molecules on the left-hand side to 2 gas molecules on the right-hand side. So that would be a decrease in entropy because you've got fewer gas molecules, so fewer ways of arranging them. Question 2. Which of the following is true for the exothermic reaction shown below? Okay, so if it's exothermic, then delta H is negative and delta S surroundings is positive. So B looks like it's true. So that looks like it should be true, but delta H positive, that's definitely not true. Delta S system, well, you're producing a gas, so it's not true that that's negative. You've got an increase in entropy of the system. And if it is a spontaneous reaction, which we know this one is, then delta S total must be positive, so it can't be that, so it must be B. Which of these solid substances is likely to have the greatest standard entropy? Use of the data booklet is not required. Well, simply from the number of atoms involved, we know that D, tin bromide or tin 4 bromide, is going to have the greatest standard entropy. It's got the most electrons out of all of those there. So bromine, a nice big atom, loads of electrons, lots of entropy, and tin bromide, the most atoms and the most electrons. So it's clearly that one there. A decrease in entropy of the system occurs when? Is it when water freezes, water boils, water reacts with sodium, or water reacts with ethanoyl chloride? Well, water reacting with sodium, we know that that makes hydrogen gas, so that would be a massive increase in entropy of the system, so it's definitely not that one, so it's not C. Water reacts with ethanoyl chloride. When it reacts with ethanoyl chloride, it's actually generating more species. So water reacting with that is going to make ethanoic acid and hydrogen chloride, from what I remember. Anyway, you've got 2 molecules becoming 2 molecules, so there's not going to be much of a change in entropy there. Water boiling, well, that's going to go from a liquid to a gas, so that would be a large increase in entropy of the system. But water freezing is liquid to solid. Those free moving particles are now constrained, so yes, A. That would be a decrease in entropy of the system. Barium carbonate decomposes in an endothermic reaction, so delta H is positive, so delta S surroundings is negative, so we know that it's going to be either B or D. And the system, we can see here, it's generating carbon dioxide gas, and so the entropy change of the system is positive, which ties in with producing a gas. So B is definitely the right answer there. Which reaction has the most positive entropy change for the system? Okay, so we've got 2 aqueous things forming something aqueous and a liquid. I mean, that doesn't look like a big entropy change, does it? So let's mark that as probably not. Here we've 2 species, which is actually 4 lots of free moving ions, is producing a solid which is fixed. That's definitely a decrease in entropy of the system. You've got 2 gases here forming a liquid. No, that's a big decrease in entropy. But here we're cracking butane into ethene and ethane. 1 gas molecule becoming 2 gas molecules. So yeah, that is a big increase in entropy of the system, so D. The reaction below is carried out at 25 degrees C. The standard entropy change of the system is. Now, if you can't do these, you are stuck, because it is products minus reactants, okay? So all we need to do is add up the entropy of the products and subtract the entropy of the reactants. So we've got 3 times 32, which is sulfur, plus 2 times water, 189, and from that we subtract the reactants. We've got 1 SO2, 248, and we've got 2 H2S, so 2 times 206, and if we work that out, the answer is minus 186 joules per mole per Kelvin. So minus 186 there. Few people getting the sign the wrong way around. The standard entropy change of the surroundings. Okay, well, I mean, the number of people that got this wrong is quite worrying. It's minus delta H over T. Now the temperature has to be in Kelvin, so it's clearly 298. We've got to remember to put delta H into kilojoules, so that's why we're multiplying it by 1,000. But the number of people who are not being careful with signs, and you are going to come unstuck, and I can only assume it's the people that don't do maths and don't see the importance of this. But delta H is minus 107.4, so it's a minus number. In other words, it is positive 107.4 times 1,000 over 298. And if you do not see the importance of this, and if you are not being careful with signs, you will get all of these wrong. Okay. Everybody but one person could be bothered to plot a graph, and that was really good to see. So plotting these against temperature, find the enthalpy change and find the entropy change. So here's my graph for the first one, again done in the space of about 2 minutes. We can see y equals minus 0.445x minus 36.5. Right, 36.5, that's clearly the enthalpy change. So the enthalpy change is 36.5 plus kilojoules per mole. And if we're putting it to two significant figures, it's plus 37. Cool. And finding the entropy change, well, there's two things we've got to remember, and many of you didn't. You can see here it's minus 0.445, the gradient. So the gradient is minus 0.445. So, first thing, the gradient is minus ds, so therefore ds is plus 0.445. Lots of people forgetting that. Secondly, this is in kilojoules per mole per Kelvin, and we need to multiply that by 1,000, so ds is 445, or into two significant figures, 450 joules per mole per Kelvin. Okay, and lots of people getting that wrong. Another example here, plotting a second graph. Again, took far less than 6 minutes to do the whole lot. 6 minutes, 6 marks. So 188x minus 195.1. So the easier one, because we can just literally use the number, is minus 195.1 kilojoules per mole for the enthalpy. That's the intercept. And what is the entropy? Well, the gradient, which equals minus ds, was plus 0.188, so therefore ds is minus 0.188, and that is in kilojoules per mole per Kelvin, so therefore delta S is actually minus 188 joules per mole per Kelvin, which to two significant figures is minus 190 joules per mole per Kelvin. Right, explain in terms of molecules why the entropy is 0 when the temperature is 0 Kelvin. And you had to talk about disorder. So the idea here is that there is no energy, so no vibration of molecules, so it's perfect order. Zero entropy. So talking about perfect order or no disorder, 1 mark. Talking about that fact there's no energy, so there's no vibration or no ways to distribute that energy is the other mark. Explain why the first part of the graph is a line that slopes up. I had lots of people talking about this changing state to a liquid, but no, the change in state here, this is melting. So why does this part of the line slope up? Well, it's because you've got more energy. So there are more ways of distributing the energy. So if you said more vibration or something like that, that was fine. So therefore there's more disorder. Explain why L2 is longer than L1. So why is this a bigger jump than this? Well, and I think most people got the right idea here. It's that liquid to gas is a huge increase in disorder. As gas molecules are much freer to move. Than solid or liquid. There's just a massive entropy increase. And if you go back and look at the entropy of ice, water and steam, you'll see it's something like 40, 70, 200. So there's a massive increase in disorder as you get gas molecules. Figure 2 shows how the free energy change for a particular gas phase reaction varies with temperature. Explain with the aid of a thermodynamic equation why this line obeys the mathematical equation y equals mx plus c. Well, you had to basically write delta G equals minus d delta S times by the temperature plus delta H. So that is the intercept and that is the gradient. And provided you wrote that equation somewhere, that was at least 1 mark there. Explain why the magnitude of delta G decreases as T increases in this reaction. This was so important, and there are a couple of massive misconceptions coming in here. Okay, it is not that delta S increases. It's not that at all, okay? Now, we know it does slightly, okay? Because from this graph all the way up here, we know that the entropy does change a little bit with temperature, and we do get a slight increase. But that is not the reason that delta G is decreasing, okay? The reason that delta G is decreasing is because delta G equals delta H minus T delta S. So even if that is constant, as the temperature goes up, then this line comes down. And all you had to say was that this must be a positive number. Okay, provided that's a positive number, as the temperature goes up, the line will follow a straight line down, okay? And it's really important you understand this. I cannot flag this up enough. Why does delta G decrease as T increases? It's not that delta S is changing. It does, but only slightly. It is because delta S is positive. That's the key thing there, and that means it's a negative line. If delta S is negative, we would get a positive gradient, and many of you, I'd say most of you, missed that key point there. State what you can deduce about the feasibility of this reaction at different temperatures. Well, again, lots of people didn't bother to pay attention to my warnings that you need to learn that here where delta G is positive, it is not feasible, but here above 500, this is where it's feasible. Okay, so what can you deduce about the feasibility of this reaction at different temperatures? It is feasible above 500K. Might seem very obvious, but so many people didn't get that right. Following reaction becomes feasible at temperatures above 5440K. Entropy is involved. Calculate the entropy change. Again, there's no reason for any of you to get this wrong. 131 plus a half of 205, that's the entropy of the products, minus the entropy of the reactants, 189, plus 44.5 joules per Kelvin per mole. So there's a slight increase in entropy. We should expect that. We're going from 1 gas molecule to 1.5 gas molecules. Calculate the value for the enthalpy change of the reaction at 5440K. Okay, so the key thing here is that the following reaction becomes feasible at temperatures above 5440K. So we know that at 5440K, delta G equals 0 equals delta H minus T delta S. In other words, the enthalpy change is T times delta S. The temperature is 5440. The entropy change in joules per Kelvin per mole is 44.5, but let's put that in kilojoules, and we get an answer of 242 kilojoules per mole, positive there. Okay, so it's an endothermic reaction. Does that make sense? Yeah, of course it is. We're splitting water into hydrogen and oxygen. We would expect that to be endothermic. We know that goes via electrolysis. Follow equation shows the formation of ammonia. Graph shows how the free energy change for this reaction varies with temperature above 240K. Use the graph to find the entropy change of the system. Give your answer in joules per Kelvin per mole. Okay, well we could go from that point there to, where should we go to? We could go all the way up to this point here, couldn't we? So what's the decrease there? Well, that's 20, 30, 40, 50, 63. So this is 63 divided by, and we've gone from 260 all the way up to 900. So that is 640. 63 divided by 640 is plus 0.098 as the gradient. Now remembering of course that ds is minus that, so ds is minus 0.098, and that is in kilojoules per mole per Kelvin. So putting that in joules, that equals minus 98 joules per mole per Kelvin. Okay, that's the entropy change. Use the graph and your answer to part A to find the enthalpy change of the reaction. Give your answer in kilojoules per mole to two significant figures. Note that no extrapolation of the line is necessary. Now, if you wanted, you could try and extrapolate the line and guess where you think that is going to hit the axis there, but there's an easier way. We know that delta G is 0 at 460 Kelvin. Therefore, we do what we did before. Delta H equals T delta S, which equals 460 times by minus 98 over 1000, and that equals minus 45 kilojoules per mole. Okay, and we got that from the fact that instead of having to extrapolate all the way down here, we know where delta G is 0, and we did the same thing that we did for our previous question, so minus 45 kilojoules per mole. Explain how the graph is consistent with Le Chatelier's principle. Okay, very few people got 2 marks out of 2 for this. As you notice here, as the temperature increases, so as temperature goes up, delta G gets more positive. In other words, the reaction gets less feasible. So what we want to say, as the temperature goes up, then delta G gets more positive. So we've got less feasible and we've got less product. What Le Chatelier would say, for an exothermic reaction, as the temperature goes up, the yield goes down because it favours the endothermic reaction, and therefore these two things agree with each other. Both of them say as the temperature goes up, you get less product. And of course now you are explaining Le Chatelier here, really, aren't you? You're using entropy to explain the fundamental basis of Le Chatelier's principle. The line is not drawn below a temperature 240 Kelvin because the gradient changes at that point. What happens? So many people were verging around that. Loads of people wrote that the reactants turn to liquid. Well, that's not right. It's not the reactants. If we have a look, it is, of course, the ammonia that condenses. And if you're saying, how do I know that? C10, okay? You know the Haber process. So you need to look at C10, the Haber process, if you didn't know that. Ammonia cools at around minus 30 degrees C, and that is how it is removed from the Haber process. Now, this was annoying. The number of people who said, where am I supposed to find these values? And that just tells me you did not do your work for the third lesson of this, where nothing was submitted. Because if you had done those questions, you would have used the data book, you would know exactly where to look for these values. So all those people that emailed me saying, I don't know where to get the values, or they're not in the data book, I know you didn't do work from that third lesson. So I have put a mark against you for that. So looking up in the data book, we can find that the values are, use data from the table to calculate the standard enthalpy change for the reaction. The number of people that couldn't do this. I mean, did you revise topic 8 for your end of year test? I seriously doubt it if you couldn't do this. That is minus 3808.8 minus, so minus 3973.8, and that equals positive 165 kilojoules per mole. Okay, such a standard question there, and if you're getting that wrong, I presume it's because you're not being careful with your units. We can do exactly the same thing for the entropy change. It's slightly easier here, so it is plus 591.1 or 591 joules per Kelvin per mole. Calculate ds total for the reaction. Right, well, we've got ds system, so ds surroundings is minus delta H over the temperature, which equals minus plus 165,000 divided by the temperature, which equals 298 minus 554 joules per Kelvin per mole, and then add that to the 591, so delta S total equals minus 554 plus 591.1, and that equals plus 37 joules per Kelvin per mole. Okay. Using your previous answers, calculate the minimum temperature at which this reaction should be feasible. Give your answer to the nearest integer. Well, delta G is 0 equals delta H minus T delta S. So the temperature is delta H over delta S. You've seen that loads of times before. The enthalpy change is 165,000. The entropy change of the system is 591.1. So let's just say 591. So the temperature is 279 Kelvin, but it asks for your answer in degrees C, so minus 273 equals 6 degrees centigrade. Okay, so that is when the reaction stops being feasible. Now, this is the minimum temperature at which the reaction is feasible. In other words, when the reaction, it's a spontaneous endothermic reaction, and when it cools down to that temperature, it should stop being feasible and the reaction should stop. In other words, it should not be allowed to cool below that temperature. So the reaction actually cools to about minus 28 degrees C before it stops being feasible. Give two reasons why this temperature is different to the temperature you calculated in there. Right, number one, not average bond enthalpies. Loads of people were talking about the fact that the bond enthalpies are average numbers, or the enthalpies are average numbers. They're not. These are enthalpies of formation. They are measured exactly. These are not bond averages. They are exact numbers. But what is true is that the values are only exact at 298 Kelvin. And delta H and delta S do change minimally with temperature, okay? There's a small change in delta H and delta S with temperature, okay? So therefore, delta G equals 0, not exact. So that's the first thing. Delta H and delta S are only exact at that temperature 298 Kelvin. As you cool down, there's slight, and I do stress slight, changes in the delta H and the delta S values. What's the other reason? Well, if we look up here, we've got barium chloride solid and H2O liquid. So the barium chloride will dissolve in the water, or you could also talk about the fact that the water will freeze. Or otherwise just talk about state changes that aren't accounted for. And that obviously means that your delta S value is wrong. Also probably means that your delta H value too. So unless the stuff is exactly what was shown there, then the delta S and delta H values are going to be wrong because it's not forming the exact products that are shown in that equation. Okay, I hope that was helpful. Enjoy Bourne Harbour cycles, and I will see you in a few weeks. Goodbye.